All right, our next talk is REVIS, an error visualization tool for Rust. And this is by Ruochen Wang, Molly MacLaren, and Michael Coblenz. And Ruochen will be giving the talk. This is a remote talk, I believe, right? So, can you hear us? Can you say something?
Hello.
Hello, yes, we hear you. Excellent. Please go ahead.
So, hello everyone. I'm Ruochen. I'm currently a PhD student at George Mason University, and today I'm presenting my work when I was a master's student at UC San Diego with Molly MacLaren and Michael Coblenz. So Rust, it came about because some traditional languages are not memory safe. For example, C and C++, they allow you to dereference pointers arbitrarily. And Microsoft found that 70% of their vulnerabilities are related to memory safety problems. So, so Rust tries to solve this problem by using an ownership and lifetime mechanism to ensure memory safety without the need of garbage collection. So you have both the safety and you do not have any performance issues. And the tricky part is that lifetime-related compiler error messages are hard to understand. So here is an example of lifetime error in Rust. We have a function example here that takes x, which is an array with 4 strings. We match on x if x matches this pattern. Then we assign x to a. Then we can do something, and otherwise we can do some other thing. After the match block, we pass an immutable reference of x into the function useX. But this is not valid in Rust, and this is the compiler command line error message that the compiler gives. We can see that the error exists because x is got moved to the variable a here, and you can only have one owner per value. So after the move, you cannot use x anymore in this position. In the compiler command line error message here, there are some good things that it shows the complete error information, and it also includes a help message that suggests you how to fix the error message. And but there are also some cons. First, often the command line error message is located in a separate window, so the user needs to context switch between their IDE and their terminal. And also the error message does not point out the lifetime ranges, which the learner needs to know when they are comprehending this error. And although this help message successfully suggests a fix to the error, it does not explain the error. So when the user came across a similar error next time, they may employ the same similar fix, but if the fix does not work, they don't know what to do. Another popular tool that people use is Rust Analyzer. Rust Analyzer is an official extension, and this is a pop-up box when you hover on the error here. And the pro is that it is shown inside the IDE, so people can see the error with their code. But in this case, the hover box overlaps with the code. So So in fact, you cannot see the code and the hover box together. And we can see how it is explaining the error. It has some location information here with some error message, which is the same as the command line error message, but they're not intuitive because we cannot see intuitively where 99 is and where 712 is. Also, the pop-up box may contain some irrelevant information, such as this unit parenthesis here, which is the return type of the usex function. And this kind of irrelevant information may interfere with the comprehending of the error. So we want to help learners understand lifetime errors with visualization. One of the existing visualization tool is REVIS, developed by Cyrus, and it is a tool used by instructors to create interactive diagrams that visualize lifetime. So it has the code on the left and the visualization on the right. It shows the lifetime of X and A. We ended up not using REVIS as our visualization scheme because we first want to automatically generate the visualization and also customize it for each error message. So I will present our tool, REVIS, an error visualization, ROS error visualizer. So our tool is a VSCode plugin that displays visualization for errors next to the user's code. We currently support 8 types of lifetime-related errors, and this is a screenshot of the tool. And next, I will play a demo. So we are in VSCode right now. There is a red triangle in the gutter that shows that there is an available visualization on line 6. To display the error, we first put a caret on the line and press the keyboard shortcuts. Then the visualization will be shown. This is the example code shown in the previous slides. There is a blue region here that shows the lifetime of X. And there is the purple arrow that shows where X is moved to another variable. This is where the X's lifetime ends. And the red arrow shows where X is used. And there's also a tip explaining the error. And when the user tries to rename the variable, they can save the file again to update the visualization. And if the user edits the code that is overlapping with the image, they can also save the file to update the image. And if the window is not wide enough, they can scroll horizontally to see the whole visualization. To hide the visualization, they can just hit the same keyboard shortcut. And next, I'll talk about the components of the visualization. The first is regions. Regions denote lifetime of variables. It starts when the variable is defined and ends when it is moved or goes out of scope. And it is shown here as a vertical line with endpoints. And regions can be open or closed. In this case, we are displaying the lifetime of this closure. And the closure starts on line 15 and extends after the function is returned. Because the endpoint is not specified, we have an open region here. So the next types of component is arrows. Arrows denote single events like borrow or move. And we show on line 9 that x is moved to another variable here. And on line 12, the use of x after being moved. We also include a tip for every error. The tips are descriptive text explaining the error, so the user knows why the error is not allowed in the Rust language. So next, I'll talk about the implementation of REVIS. It is implemented as a VSCode extension, and the visualizations are SVG images. We generate the visualization from a structured Rust compiler output. So, so we depend on the Rust analyzer extension, and Rust analyzer will run the Rust compiler every time the file is saved, and we parse the generated Rust compiler output. So when we get the output, we first look at the error code shown here. And if this is a supported error code, we will use the location and message information to locate the lifetime start and end points and the move and borrow actions. Once we compute the SVG image, we attach it to the proper line as a line decoration. So next, I'll talk about the user study. We performed a user study in a compiler constructions course, where most students are introduced to Rust for the first time, and they constructed a compiler gradually with several programming assignments. The study lasted from week 6 to 10 of the quarter, and during the time, students completed 3 programming assignments, which including heap allocation, garbage collection, and optimization. So for the participants, we asked them to install a build.r script that automatically saves the whole project every time the compiler is run. And we gather all the build versions to our machine, and we build each version to obtain the errors. After that, we calculate the resolution time of each error. And that is from when the error first appears until the error disappears. And we randomly assign our participants to use or not use REVIS. After the study, we give them an exit survey on programming experience and the experience using the tool. So we gathered over 6,000 commits from 6 students, and over 15,000 instances of error messages. But only 51 of them are supported by REVIS. That is 0.3%. But we found that they take 3.4%, so 10 times the program repair time. So so we can see that there is some uniqueness in Rust that causes more repair time than regular error messages. And in the survey, we 2 out of 3 students which were assigned to use REVIS said it was useful. And the other student reported having written 10,000 lines of Rust before the study. So the tool may only be useful for new Rust users. And on future work, because we only had 6 students in the study, we did not perform an evaluation of the usefulness of the tool. We're hoping to perform a larger scale evaluation that is conducted in a general programming scenario to evaluate the tool. So one reason why there are so few lifetime-related errors in our results may be that in the programming scenario, it is a Rust. They are building a compiler, and the compiler is built in a rather functional way. So there are so most of the references are immutable references. So there may be fewer lifetime-related errors in that case. And we are also hoping to support more error codes and improve the descriptions. So apart from lifetime-related errors, there are also some other kinds of errors that are unique to Rust, such as trait-related errors. And also, we are hoping to add an opt-in data collection component, which can help the user to understand how they are coding, and also help us to collect data more conveniently. And that's all. Thank you.
Thank you. We have time for a few questions.
Thank you for the talk. So in the 99.7% of other errors that you saw from your study, I'm curious what were the most common errors encountered by your 6 participants in the study?
The most common, I think, is the syntax error. And it is the syntax error, and I think that is consistent with other studies that people performed. Like they also found that syntax errors are the most prevalent kinds of errors.
Got it. Thanks.
All right. Maybe people can introduce themselves since the speaker is remote.
Gavin Gray. So in the visualizations that you propose, there's a very strong reliance on like the linearity of a lifetime, but lifetimes in Rust can be nonlinear, right? And be sets of program points. And so how might you extend this visualization to encapsulate those types of errors?
So yeah, currently we only support this kind of lifetime. Yeah, and for example, if the lifetime is related to another function or another like type definition, so first we need to figure out a way to display the visualization across different places of the code, so the user can scroll between different positions of the code. So we'll probably first display all the related code together, and related to visualization, we may draw like boxes or draw boxes around the the variable to show if it is owned or borrowed, and with that to help the users.
Okay, thanks.
Other questions? I have a question. This is Jonathan Aldrich from Carnegie Mellon. I was wondering if there was a design process that went into the development of the visualizations. Did you try different alternatives? Did you get any feedback on that?
And the design process, I think we just like design the visualization as we are talking, and we did not iterate many like versions of the visualization.
Okay, thanks. Well, it definitely looks very, I mean, it looks very clear intuitively, so it's a nice design.
Yeah, about the visualization, I did not know you could embed an SVG in VSCode. That's crazy. Can you basically, okay, because I've been harping on the inability to like do arbitrary decorations in VSCode for a long time. But can you basically, does the SVG mechanism let you draw arbitrary images over the entirety of your VSCode region?
So the SVG is attached to one line of the code, and so you first, I think you can also attach like PNG images and other types of images. And I think there is a API in VS Code extension. I think it's text decoration, and you can specify that the decoration is attached to the whole line, and it is displayed after the line ends. So, so the visualization also moves with the code if you scroll and zoom in or zoom out.
So you generate an SVG like per line of VS Code that you're inserting into. There's not like one SVG that you like draw over the whole region.
No, that is the one single SVG attached to one line, and it is displayed.
Oh, but that SVG can span
higher.
multiple lines. Wow.
Yeah.
Interesting. All right, thank you.
Those are comments that you want to share that with the speaker?
So to share comments with the speaker, Eric Gama is my homeboy. 20 years ago, they used to use a book called, what was it called? Design something. That's it, yeah. Design patterns. And who was the first author? Eric Gama, that's right, yeah. And, you know, he was like in Switzerland, and he did this domain analysis of three main frameworks, one of which, he did the domain analysis, it wasn't his PhD, two of which were done in C, one of which was done in Smalltalk about how you should do display editors. And this is the secret to having a happy and successful academic life, is always keep doing the same thing from your PhD onwards. Famously, Rustin Leno has been writing the same program since he was 12. I lied, he was probably about 18 or 20 maybe when he started, and he's still doing the same thing today. And Eric Gama did his PhD on analysis of these kind of frameworks, and then he went to a big blue company called IBM and wrote something called Eclipse. And then when he'd finished with that, when they stopped giving him enough money, he got more money from Microsoft and wrote Visual. Is this right? I think this is right. Yeah, anyway.
All right, I have one more question. This is really cool, and I think it's. I mean, it makes a lot of sense to start with this, both because it's a nice visual. There's a visual aspect to this, to lifetimes, and because, as you showed, they're like, high. Even though they're a small percentage of errors, I was surprised at how small they were. They took 10 times the average amount. I'm wondering, are there other errors that you're looking at in Rust or anywhere really that kind of fall into this category of being hard but also possibly amenable to visualization?
I think this kind of method can apply to errors with a kind of live timeline, and like there are some concept that has start or end points that can be easily visualized. And but currently, we're just looking at lifetime errors. I think there will be some other types of errors that can also be visualized in this way. Yeah, that's an interesting future work direction.
Yeah, thank you.
So we have a follow-up project which Molly is working on to get a much sort of deeper and broader analysis of errors that people experience in Rust. So this is done in the context of a course. We're looking at deploying this sort of out in the world, and then doing a bunch of analysis of statistics of the errors that people produce, and okay, which ones are worth addressing, and how can we address those. But the idea is to sort of prioritize which ones we work on according to the ones that people really spend time on. Did you want to say anything?
Yeah, so during the study, we actually found that, in fact, the most common was undefined references. So, and this was across also in other studies from Java and C. And we were also interested in if that's like a byproduct of the coding experience. Like if you're defining, if it's like a legitimate error, like you've mistakenly forgot to define something and now you're trying to reference it, or if it's like just a part of if errors are used as like a task list. And then kind of an extension onto this is we wanted to actually integrate the error recording and error logging with the extension so that users that are currently using REVIS can actually opt into our study, and then we can get error data from all different contexts, not just our course at UCSD. And so hopefully we can get more information there, and also even use this to host other Rust tools and get feedback on those. And so it's kind of like the start of a really big project.
Great, thank you. All right, yes, we should wrap up. So let's thank Ruochen again.